74,000 years ago, on an island in what we now call Sumatra, a mountain that had stood silent for millennia began to tremble. The people living nearby, our ancestors, would have felt the earthquakes, seen the steam rising from cracks in the earth. Perhaps they sensed that something was wrong. But nothing could have prepared them for what happened next. The mountain didn't just erupt. It exploded with a violence that defies comprehension. In a matter of hours, 700 cubic miles of rock and ash were hurled into the sky. The eruption column punched through the atmosphere itself, reaching heights where the air is too thin to breathe. And then the sky went dark. Not for a day. Not for a week. For years. The ash spread across the entire planet, carried by winds that knew no borders. It fell like black snow on forests and grasslands thousands of miles away. It buried the sun. And when the sun disappeared, the world began to freeze. Temperatures plummeted. In some regions, they dropped by 15 degrees Celsius. Imagine that. 15 degrees. Enough to turn summer into winter. Enough to kill crops before they could grow. Enough to starve entire ecosystems. The volcanic winter lasted for a decade, perhaps longer. We cannot know for certain because there was no one left to write it down. What we do know comes from genetic evidence. DNA studies suggest that during this period, the entire human population collapsed to between 3 and 10,000 individuals. 3,000 people on the entire planet. We were not yet the dominant species. We had no cities, no agriculture, no technology beyond stone tools and fire. We were vulnerable. And we came terrifyingly close to extinction. Some scientists believe that Toba created what geneticists call a population bottleneck, a moment when our species was reduced to such small numbers that every person alive today, all 8 billion of us, is descended from those few thousand survivors. We are here because they endured. Because somehow, in the cold and the darkness and the hunger, they found a way to survive. But here is the question that should keep us awake at night. What if it happens again? Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. There are mountains on this Earth that are not mountains at all. They rise from the sea, crowned with snow. They stand watch over cities, silent and ancient. Farmers plant their fields on their slopes. Children play in their shadows. But beneath the soil, beneath the stone, beneath centuries of quiet, something waits. For most of human history, we did not understand them. We saw only what they showed us: beauty, fertility, permanence. The Romans built Pompeii at the foot of Vesuvius and called it paradise. The richest vineyards. The warmest winters. A mountain that had not stirred in living memory. They had no word for volcano. They had no reason to fear. On the morning of August 24th, in the year 79 AD, the mountain spoke. And when it finished speaking, 17 hours later, 2 entire cities had vanished. 16,000 souls. Gone. Not by lava, not by fire alone. By something the Earth had kept hidden for 1,000 years. That eruption changed nothing about the mountains themselves. But it changed everything about how we see them. Because Vesuvius taught us a truth that geologists would spend 2 millennia trying to fully understand. Some volcanoes don't just erupt. They annihilate. Today, we know there are approximately 1,500 active volcanoes on Earth's surface. Most will never harm anyone. They breathe. They grumble. They release pressure slowly, gracefully. But among them, hidden in plain sight, are a dozen giants that do not play by these rules. Volcanoes that have, in the past, plunged the entire planet into darkness. Volcanoes that have rewritten the climate, collapsed civilizations, and brought our species to the edge of extinction. And the question that haunts every volcanologist is not if one will awaken again. It is when, and which one. To understand whether a volcano can truly destroy the world, we must first understand what destroy means. Not in the language of Hollywood, not in the poetry of ancient myths, but in the cold, precise calculations of modern science and in the fragile testimony of those who have stood too close. When the Earth decided to remind us, we are guests here. And a lease has never been permanent. To answer whether a volcano can destroy the world, we must first ask what makes a volcano capable of such devastation. The answer lies not in the size of the mountain we see above ground, but in what sleeps beneath it. And in a classification system that most people have never heard of, but which separates a mere eruption from a planetary catastrophe. It is called the Volcanic Explosivity Index, the VEI, On this scale, most eruptions never rise above a 3 or 4. They are local events. Tragic perhaps for those nearby. But contained, manageable, the Earth clearing its throat. A VEI-5 eruption, like Mount St. Helens in 1980, can flatten forests for miles. It can send ash across a continent. 57 people died that day, and the mountain itself lost over 1,000 feet of height in a single explosive breath. We called it a catastrophe. We were wrong. It was merely a warning shot. A VEI-6 eruption is something different entirely. In 1883, a volcanic island called Krakatoa, sitting between Java and Sumatra, detonated with a force equivalent to 200 megatons of TNT. The sound of the explosion traveled around the world 4 times. It was heard 3,000 miles away. The pressure wave altered barometers in England. The eruption generated tsunamis over 100 feet high. 36,000 people drowned, most of them while they slept, in villages that had stood safely above the tide for generations. But here's what truly matters. Krakatoa ejected 5 cubic miles of material into the atmosphere. Ash and sulfur dioxide climbed into the stratosphere and stayed there for years. Global temperatures dropped. Sunsets turned blood red across Europe and America. Crops failed. The world darkened. And Krakatoa was only a 6 on the scale. A VEI-7 eruption occurs on average once every 1,000 years. The last one happened in 1815. Mount Tambora in Indonesia. It released 40 cubic miles of ash and rock. The eruption column reached the stratosphere and spread across the entire planet. The following year became known as the year without a summer. Snow fell in June across New England. Crops died in the fields across Europe. Famine spread like a plague. In Switzerland, people ate cats and grass to survive. Riots erupted over bread. Typhus and cholera followed hunger. Mary Shelley, trapped indoors by the endless gray skies during a vacation in Geneva, passed the time writing a novel. She called it Frankenstein, a story about man playing God, about creation and consequence, about a monster that could not be controlled. The monster was real. It just wasn't made of stitched flesh. It was made of sulfur and ash and the terrible indifference of the earth itself. Tambora killed over 70,000 people directly. The famine and disease it triggered may have killed 10 times that number. And still, we have not yet reached the summit of what is possible. A VEI-8 eruption is called a supereruption. It requires the ejection of more than 240 cubic miles of material. More than 1,000 cubic kilometers of earth and rock and magma hurled into the sky. These eruptions do not happen on human timescales. They happen on geological timescales. They are measured not in decades or centuries, but in tens of thousands of years. But they do happen. 74,000 years ago, a volcano named Toba, in what is now Sumatra, experienced a supereruption. It released 700 cubic miles of material. The ash layer it left behind can still be found in ice cores from Greenland. In sediment cores from the Indian Ocean, the global temperature dropped by as much as 15 degrees Celsius in some regions. The volcanic winter lasted for years, perhaps a decade. Some scientists believe that Toba brought humanity to the brink of extinction. Genetic evidence suggests that the entire human population may have been reduced to as few as 3,000 to 10,000 individuals. A bottleneck so severe that we are all, every person alive today, descended from that tiny group of survivors. We do not know this with certainty. The evidence is debated. But what is not debated is this. Toba reshaped the planet. And it can happen again, so can a volcano destroy the world? The answer depends on what we mean by world. If we mean the planet itself, the spinning ball of rock and magma and water, then no. Earth has survived far worse. It will outlast us by billions of years. But if we mean the world as we know it, the fragile systems that keep 8 billion people fed and sheltered and alive, then the answer is far less comforting. A supereruption would not need to kill us directly. It would only need to disrupt the systems we depend on. The agriculture, the supply chains, the climate stability we have built our entire civilization upon. And somewhere on this planet right now, the conditions for such an eruption are quietly assembling. Magma is rising, pressure is building, calderas are swelling. The giants are stirring in their sleep. And we are only just beginning to learn how to listen. If you ask someone to picture a volcano, they will likely describe a mountain. Tall, conical, smoking at the peak. Vesuvius, Fuji, the classic silhouette that has defined our understanding for centuries. But the most dangerous volcanoes on Earth do not look like mountains at all. They look like lakes, like valleys, like gentle rolling hills where cattle graze and tourists take photographs of wildflowers in spring. They are called calderas, and they are the scars left behind when a volcano does not simply erupt, but collapses into itself after emptying its entire magma chamber in a single cataclysmic event. What remains is not a peak, but a depression. A crater so vast that you can stand inside it and never realize you are standing inside a volcano at all. These are the sleeping giants. And we have only recently learned to recognize them. In 1965, two geologists, Bob Christensen and Howard Wilcox, were studying satellite imagery of Yellowstone National Park. They were looking for the volcano that had produced the area's distinctive thermal features. The geysers, the hot springs, the bubbling mud pots. Everyone knew there had been volcanic activity in Yellowstone's past. But where was the volcano? It was Christensen who finally saw it. Not by looking closer, but by pulling back. By viewing the entire park from above. The volcano was not inside Yellowstone. The volcano was Yellowstone. The entire park, an area of nearly 3,500 square miles, sits inside a caldera. A crater so enormous that it can only be fully perceived from space. The boundaries are marked by cliffs and ridges, but to someone standing inside, it simply looks like landscape. Beautiful, peaceful, benign. Beneath that beauty lies a magma chamber 37 miles long, 18 miles wide, and up to 10 miles deep. It contains enough molten rock to fill the Grand Canyon 11 times over. Yellowstone is not a mountain that might erupt. It is a supervolcano that has erupted 3 times in the past 2 million years. The last eruption 640,000 years ago was 1,000 times more powerful than Mount St. Helens, and every measurement suggests it will erupt again. Yellowstone is not alone. In southern Italy, just west of Naples, lies another caldera, Campi Flegrei. The Phlegrean Fields, a sprawling area of volcanic craters, bubbling fumaroles, and ancient ruins built by Romans who had no idea they were living atop a powder keg. Campi Flegrei last erupted in 1538, a relatively minor event that built a new hill in just 1 week. But its previous major eruption, 39,000 years ago, was a VEI-7. It ejected ash across the Mediterranean. Some scientists believe it may have contributed to the extinction of the Neanderthals in Europe. Today, over 500,000 people live directly above this caldera. The city of Pozzoli on its edge has experienced episodes of bradyseism, where the ground rises and falls by several meters over the course of months or years. The earth breathing. In recent decades, the ground has been rising more frequently. Seismic activity has increased. The magma chamber is restless. Italian authorities monitor it constantly. But monitoring is not the same as controlling. And evacuation plans for 500,000 people are, at best, optimistic. In New Zealand, there is Lake Taupo. It is the largest lake in the country, a serene body of water beloved by fishermen and tourists. It fills a caldera created by one of the most violent eruptions in human history. In the year 232 AD, Taupo produced a VEI-7 eruption. The explosion was so powerful that pumice and ash were ejected at supersonic speeds. Pyroclastic flows traveled over 50 miles from the vent. The ash cloud was visible from China. The Maori, who would not arrive in New Zealand for another 1,000 years, inherited only the myths of fire in the sky passed down by distant observers. Today, Taupo is quiet. The lake is deep and cold, but beneath it, magma continues to accumulate. Slowly, patiently. And in the Pacific Ocean, spanning much of the North Island of New Zealand, geologists have identified the Taupo volcanic zone, one of the most active volcanic regions on Earth. 25 eruptions in the past 12,000 years, some small, some catastrophic. The pattern is clear. The question is only timing. Perhaps the most haunting of all is Lake Toba in Sumatra. The lake is over 60 miles long and nearly 1,900 feet deep. It is one of the most beautiful places on Earth. Tourists visit for its tranquility. Local Batak people have lived on its shores for centuries. Fishing its waters, farming its fertile soils. Few realize they are living inside the crater of the most devastating volcanic event of the past 75,000 years. The Toba supervolcano erupted 74,000 years ago with a force almost beyond comprehension. It ejected an estimated 700 cubic miles of material. Ash layers from this eruption have been found in ice cores from Antarctica, sediment cores from the Arabian Sea. The sulfur dioxide released into the stratosphere triggered a volcanic winter that may have lasted for a decade. Some climate models suggest global temperatures dropped by as much as 15 degrees Celsius. Genetic evidence suggests that human populations crashed during this period. We may have come terrifyingly close to extinction. Toba has not erupted since, but the magma chamber remains. And geological evidence shows that these supervolcanoes operate on cycles. Long cycles. Cycles measured in tens of thousands of years. Which means, by the cruel mathematics of probability, we are closer to the next super eruption now than we were 74,000 years ago. These calderas share a common trait. They hide in plain sight. They do not announce themselves. They do not tower over the landscape in menacing silhouette. They blend into the world we think we know. And that is precisely what makes them so dangerous. Because a threat we cannot see is a threat we do not prepare for. And a threat we do not prepare for is a threat that will catch us. Exactly as it caught the people of Pompeii. Asleep. Unaware. Trusting in the permanence of the ground beneath our feet. But the ground is not permanent. It never was. And beneath these lakes, these valleys, these tourist destinations, the monsters are waking. To understand how a volcano could alter the fate of humanity, we must first understand what happens when one of these giants awakens. It begins quietly, invisibly. Deep beneath the Earth's crust, in chambers that dwarf any cathedral, molten rock accumulates, magma. Not the fast-flowing lava we see in films, but something far more dangerous. A thick, viscous mixture of molten minerals. Dissolved gases and crystals suspended in a solution of unimaginable pressure and heat. For thousands of years, this magma rises slowly through cracks in the bedrock. Millimeter by millimeter. Century by century. The chamber fills. The pressure builds. The rock above bends and swells like a blister on skin. And then, at some unpredictable threshold, the rock can hold no more. What follows is not merely an eruption. It is a decompression event of planetary scale. When the confining rock finally fails, the gases dissolved in the magma, carbon dioxide, water vapor, sulfur dioxide, suddenly find themselves free to expand. They do so explosively. Imagine opening a bottle of champagne. Now imagine that bottle is 30 miles wide and contains not wine, but magma at temperatures exceeding 800 degrees Celsius. The initial blast can exceed the speed of sound. The eruption column, a churning mixture of ash, rock, and gas, rockets upward at hundreds of miles per hour. It can reach the stratosphere in minutes. In the largest eruptions, it can punch through the troposphere entirely and climb to heights of 30 miles or more. At these altitudes, the ash and sulfur aerosols spread horizontally, carried by stratospheric winds. Within days, they can encircle the globe. Within weeks, they form a veil that dims the sun itself. This is not science fiction. This is not speculation. This is what happened at Tambora, at Krakatoa, at every major eruption in recorded history. And in a supereruption, the scale is simply multiplied by a factor that defies intuition. But the eruption column is only the beginning. As magma continues to pour from the vent, the chamber below begins to empty. And when enough material has been ejected, the roof of the chamber, the miles of rock that once supported the mountain above, loses its foundation. It collapses. Not slowly. Not gradually. In a matter of hours, sometimes minutes, the entire structure falls into the void below. The ground itself opens. Mountains disappear. And the collapse generates a new wave of destruction. Pyroclastic flows. These are not rivers of lava. Lava is slow, predictable. It flows downhill like thick honey, giving people time to flee. Pyroclastic flows are avalanches of superheated gas and rock fragments that race down the flanks of the volcano at speeds exceeding 100 miles per hour. They incinerate everything in their path: trees, buildings, people. The temperature inside these flows can exceed 700 degrees Celsius. There is no outrunning them. There is no shelter from them. The only defense is distance, and most people do not have enough warning. At Pompeii, it was not the lava that killed 16,000 people. It was the pyroclastic surges that swept down from Vesuvius. In the middle of the night, Most victims died instantly, their lungs seared by the superheated air. Their bodies were buried in ash, entombed in the positions they held at the moment of death. Mothers clutching children. Families huddled together. A man covering his face with his hands as if that could protect him from the fury of the earth. When archaeologists uncovered these remains 1,800 years later, they poured plaster into the voids left by decomposed bodies. What emerged were sculptures of final moments. Agony frozen in time, these were not warriors. They were not explorers who ventured into danger. They were ordinary people who committed the simple crime of living near a mountain they thought was sleeping. And the mountain gave them no chance to correct that mistake. But even pyroclastic flows are localized. Deadly within 100 miles, perhaps. Catastrophic for a region. But not globally destructive. The true planetary threat comes from what lingers in the stratosphere long after the eruption ends: sulfur dioxide. When magma reaches the surface, it releases vast quantities of this gas. In the stratosphere, sulfur dioxide reacts with water vapor to form sulfuric acid aerosols. Tiny droplets that remain suspended in the atmosphere for years. These aerosols reflect sunlight back into space. They act as a shield, dimming the sun's radiation before it can reach the Earth's surface. After the eruption of Mount Pinatubo in 1991, global temperatures dropped by 0.5 degrees Celsius for over a year. Crops failed. Weather patterns shifted. A supereruption would inject hundreds of times more sulfur into the atmosphere. The cooling would not be measured in tenths of a degree. It would be measured in degrees, plural, and it would last not for months but for years, perhaps a decade. This is what scientists call a volcanic winter. The term is sterile, clinical. It does not convey what it would actually mean. It would mean shorter growing seasons, failed harvests across the temperate zones where most of the world's grain is produced. It would mean food shortages, price spikes, hoarding, panic. Modern civilization depends on a global food system operating at near maximum efficiency. We have optimized for abundance, not resilience. Most nations maintain only a few months of grain reserves. We have no buffer, no margin for error. A volcanic winter would expose that fragility immediately. And in a world of 8 billion people, all competing for suddenly scarce resources, the eruption itself would be only the first catastrophe. What follows would be famine, migration, conflict, the unraveling of the systems we have built over centuries. This is how a volcano destroys the world. Not with fire and brimstone alone, but with cold and darkness and hunger. Not by killing everyone directly, but by severing the invisible threads that hold our civilization together. The Romans, watching Vesuvius bury Pompeii, thought they were witnessing the anger of the gods, a punishment. A message. We know better now. We understand the mechanics, the chemistry, the physics. But knowledge does not grant immunity. And the next time a supervolcano awakens, it will not ask whether we are ready. It will not wait for us to prepare. It will simply erupt. And we will be forced to answer a question our species has never had to confront. Can we survive what the Earth decides to unleash? There is a place in America where the Earth's heartbeat is visible. Where boiling water erupts on schedule, as reliable as any clock. Where the ground is painted in colors that belong on another planet. Brilliant oranges, electric blues, sulfurous yellows. Where bison graze on meadows warmed by the heat rising from below. Over 4 million people visit Yellowstone National Park each year. They come for the geysers. For Old Faithful, erupting every 90 minutes with the precision of a metronome. They come for the wildlife, the pristine wilderness, the reminder of what America looked like before we paved it. Few of them realize they are standing inside one of the most dangerous geological features on Earth. Fewer still understand that Yellowstone is not dormant. It has never been dormant. It is simply waiting. The Yellowstone hotspot has been active for at least 17 million years. It is not a volcano in the traditional sense. It is something stranger, something more persistent. Deep beneath the North American continent, a plume of superheated rock rises from near the boundary between the Earth's mantle and its core. This plume is stationary, but the continent above it is not. North America drifts slowly westward, riding the tectonic plate like a passenger on a conveyor belt. As the continent moves, the hotspot burns through it like a blowtorch through paper. It leaves behind a trail of calderas stretching from eastern Oregon across southern Idaho to its current position beneath northwest Wyoming. Yellowstone is merely the latest wound. And the geological record shows that this hotspot erupts with terrifying regularity. Major eruptions occurred 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. The intervals are not exact, but the pattern is unmistakable. And by that pattern, Yellowstone is overdue. The last major eruption created the caldera we see today. 640,000 years ago, the Yellowstone supervolcano ejected 240 cubic miles of material. The eruption was 1,000 times more powerful than Mount St. Helens. Ash from that eruption has been found in fossil beds across North America, in California, in the Gulf of Mexico, in layers that paleontologists study to understand why certain species suddenly disappeared from the fossil record. The ash cloud was so dense that it turned day into night across half the continent. It buried the Great Plains under feet of volcanic debris. It choked rivers. It collapsed roofs. It smothered forests. And it reshaped the landscape so completely that if we could somehow travel back to witness it, we would not recognize the geography. Mountains disappeared, valleys formed. The continent itself was rewritten. This is not ancient history by geological standards. 640,000 years is a blink, an instant. And beneath our feet, the conditions that produced that eruption are slowly, inexorably reassembling. Today, the United States Geological Survey monitors Yellowstone with an intensity reserved for only the most dangerous places on Earth. Seismometers detect the constant tremors that ripple through the caldera. Most are minor, magnitude 2 or less, unfelt by tourists photographing bison. But they reveal what is happening below: magma moving, rock fracturing, pressure redistributing. GPS stations measure the ground's deformation with millimeter precision. In some areas, the caldera floor rises and falls by several inches per year. This is called caldera breathing, the magma chamber swelling and contracting like lungs. Between 2004 and 2010, parts of the caldera rose by nearly 10 inches. Then the inflation slowed, then reversed. The ground sank back down. Scientists do not fully understand these cycles. They do not know what triggers the inflation or what causes it to stop. They only know that it happens and that it reflects changes in the magma chamber below. Changes that could, in the worst scenario, precede an eruption. But monitoring is not prediction. And prediction is not prevention. The USGS cannot tell us when Yellowstone will erupt. They only tell us that it will, eventually, based on its history. Could be in 1,000 years. Could be in 10,000. Could be tomorrow. The probability of a super eruption in any given year is estimated at 1 in 730,000. Those are reassuring odds. The same odds as being struck by lightning twice in your lifetime. But probability is not destiny. And low odds do not mean zero odds. In 2014, a researcher noticed something unusual in the thermal readings from Yellowstone Lake. The water temperature in certain areas had increased significantly. New hydrothermal vents had opened on the lake floor. It made headlines. Yellowstone heating up, supervolcano alert. The stories wrote themselves. The USGS issued reassurances. This was normal variation. This was not a precursor to eruption. The magma chamber showed no signs of the massive inflation that would precede a catastrophic event. They were probably right. Almost certainly right. But probably is not a word that brings much comfort. When the stakes involve the potential death of millions and the collapse of civilization. If Yellowstone were to experience another super eruption, the immediate devastation would be absolute within a radius of 600 miles. Montana, Wyoming, Idaho, parts of Colorado, Utah, and the Dakotas would be buried under feet of ash within hours. Pyroclastic flows would incinerate everything within 100 miles of the caldera. The heat alone would ignite forests across the region. But the real catastrophe would unfold in the weeks and months that followed. Ash would contaminate water supplies across the western United States. It would clog air filters in vehicles and aircraft. It would collapse roofs. It would coat solar panels, rendering them useless. It would smother crops still in the fields. And then the ash would reach the stratosphere and the cooling would begin. Global temperatures could drop by 10 degrees Celsius or more. Growing seasons would shorten. Monsoons would fail. Snow would fall in summer across the northern hemisphere. The United States produces nearly 20% of the world's grain exports. that production would cease. And in a globalized world where food shortages in one region trigger price spikes everywhere, the consequences would cascade. This is not fear-mongering. This is what the geological record shows happened in previous super eruptions. And this is what climate models predict would happen again. There's a strange comfort in the fact that Yellowstone's next eruption will most likely not be a super eruption. Statistically, smaller eruptions are far more common. A VEI-5 or 6 event is far more probable. Still devastating. Still deadly within the immediate area. But not civilization ending, and the USGS has contingency plans. Evacuation routes. Coordination with FEMA. Protocols for managing the unmanageable. But plans are not guarantees. And in the calculus of disaster, hope is not a strategy. Yellowstone will erupt again. That is not a question. The only questions are when and how large and whether we will have enough warning to do anything more than watch. Because in the end, we cannot stop a volcano. We can only bear witness to its power, and hope that when the earth decides to speak, it chooses to whisper rather than scream. In the summer of 1816, the world learned what it meant to live without summer. It began with cold. Unseasonable cold that crept across Europe and North America in May. Just as farmers were planting their crops. Frost came in June. Snow fell in July. By August, the harvest had failed. In New England, farmers watched their corn wither in fields dusted with ice. In Ireland, the potato crop collapsed entirely. In Switzerland, the price of grain tripled, then quadrupled. Families who had never known hunger suddenly could not afford bread. Riots erupted in France. Grain stores were looted. Governments struggled to maintain order. Typhus spread through populations weakened by malnutrition. Cholera followed. This was not a war. Not a plague sent by human hands. This was the consequence of a single mountain 7,000 miles away. That had erupted the previous year, Mount Tambora, a VEI-7 eruption. And the year without summer was not an anomaly. It was a preview. In 1816, the world's population was roughly 1 billion people. Most lived in agricultural societies. Most grew their own food or obtained it from nearby farms. Supply chains were local, regional. If a harvest failed in New England, it did not affect the price of rice in China. Today, we live in a fundamentally different world. 8 billion people. Most of us live in cities, divorced from the land that feeds us. We do not grow our own food. We do not store grain for the winter. We trust in systems, vast and invisible systems that bring food from farms thousands of miles away to the shelves of our supermarkets. These systems are marvels of efficiency. They operate on thin margins, optimized for cost and speed. Just-in-time delivery, minimal stockpiles, maximum throughput. They are also terrifyingly fragile. Modern agriculture depends on predictable weather, stable temperatures, reliable rainfall, growing seasons that have remained roughly consistent for the past 10,000 years, the entire span of human civilization. We have optimized our crops for these conditions. Our wheat, our rice, our corn. They are bred for maximum yield under the assumption that the climate will cooperate. But a super eruption does not cooperate. When sulfur aerosols fill the stratosphere and dim the sun, temperatures drop. Frost arrives earlier in autumn and lingers later into spring. The growing season shrinks, and crops that were engineered for abundance suddenly fail. After Tambora, the growing season in parts of Europe shortened by 6 weeks. 6 weeks. That was enough to trigger famine. A super eruption would shorten it far more. The global food supply operates on a precarious balance. In a typical year, the world produces just enough grain to feed everyone, with a small surplus held in reserve. Those reserves, maintained by governments and commodities traders, amount to roughly 74 days of global consumption. 2.5 months. That is our buffer. That is the margin between abundance and crisis. If a super eruption were to reduce global harvests by even 20%, those reserves would evaporate in weeks. Prices would spike. Exporting nations would close their borders, hoarding food for their own populations. Importing nations would face immediate shortages. And shortages lead to panic. Panic leads to hoarding. Hoarding exacerbates the shortages. This is not speculation. We have seen it happen. In 2008, when rice prices spiked due to drought and speculation, food riots erupted in over 30 countries. Governments fell, people died. And that was during a time of relative stability with no volcano involved. But food is only the beginning. A super eruption would disrupt transportation networks across the globe. Volcanic ash is not like snow. It does not melt. It is composed of tiny fragments of rock and glass, sharp enough to damage engines. After the eruption of Eyjafjallajökull in Iceland in 2010, a relatively minor event, European airspace was closed for 6 days. 10 million travelers were stranded. Airlines lost billions, supply chains ground to a halt. That eruption ejected only a fraction of a cubic mile of ash. Most of it fell harmlessly into the ocean. A super eruption would eject hundreds of cubic miles. Ash would blanket entire continents. Airports would close, not for days, but for weeks. Perhaps months. Air travel, the circulatory system of the modern global economy, would cease. And with it would go the transport of not just people, but medicine, electronics, machinery, all the goods that allow our civilization to function. Consider the power grid. Much of the world's electricity is generated by coal or natural gas plants. These plants rely on air filtration systems to keep their turbines running. Volcanic ash clogs those filters within hours. In the Philippines, after the eruption of Mount Pinatubo, power plants shut down across Luzon, electricity was rationed for months, and that was one island with external aid available. In a super eruption scenario, the ash would be global. There would be no unaffected regions to send aid. Every nation would be struggling with the same crisis simultaneously. No electricity means no refrigeration, spoiled food. No water pumps, contaminated water. No communication networks. Isolation, panic. The infrastructure we take for granted, the invisible systems that keep us alive, would begin to fail, not all at once, but piece by piece. A cascade of failures, each one triggering the next. And then there is the human response. History teaches us that when resources become scarce, societies do not necessarily band together. Sometimes they fracture. Sometimes they turn on each other. In a modern context, with nuclear-armed nations competing for suddenly scarce resources, the potential for conflict is incalculable. Wars have been fought over far less than the survival of entire populations. This is how a volcano destroys the world. Not with a single dramatic blow, but by unraveling the threads that hold our civilization together. We have built a world of breathtaking complexity and equally breathtaking vulnerability. A world that depends on stability, on predictability, on the assumption that the Earth will continue to provide the conditions we need to survive. But the Earth makes no such promises. It has never made such promises. And the geological record shows, with uncomfortable clarity, that the stability we have enjoyed for the past 10,000 years is not the norm. It is the exception. The question is not whether a super eruption will happen again. The question is whether when it does, we will be ready, or whether we will be like the people of Pompeii, caught unaware, trusting in a permanence that was never real. On June 12, 1991, a farmer on the island of Luzon in the Philippines felt the ground tremble beneath his feet. It was not the first tremor. For weeks, the earth had been restless. Small earthquakes. Steam venting from the slopes of Mount Pinatubo. A mountain so quiet for 500 years that it had become background, a geographical feature rather than a threat. But now, geologists from the Philippine Institute of Volcanology and Seismology were paying attention. And what they saw in their instruments terrified them. Magma was rising. Fast. Within days, they had installed a network of seismometers around the volcano. They measured gas emissions. They tracked ground deformation. And they made a decision that would save tens of thousands of lives. They issued an evacuation order. On June 15, 1991, Mount Pinatubo erupted. A VEI-6 event. The second largest eruption of the 20th century. Pyroclastic flows raced down the mountain at over 60 miles per hour. Ash buried entire towns. The eruption column reached 22 miles into the stratosphere. But the towns were empty. Because the people had been warned, 58,000 people had been evacuated from the danger zone. Hundreds of thousands more had fled from the broader region. The eruption killed approximately 800 people. Most of those deaths came from collapsing roofs, weighed down by ash mixed with rain from a typhoon that happened to strike the same day. Tragic, but not the tens of thousands that would have died had they remained in their homes. Pinatubo was a triumph of modern volcanology. Proof that monitoring works, that science can save lives. But it was also a reminder of how little time we have when a volcano finally decides to wake. Today, approximately 800 million people live within range of an active volcano. Not all of these volcanoes are monitored. In fact, most are not. The United Nations estimates that only a fraction of the world's active volcanoes have any real-time monitoring equipment at all. The reasons are simple: cost, infrastructure, and political will. Seismometers, GPS stations, gas analyzers, satellite monitoring systems. These technologies exist. They work, but they are expensive. Convincing governments to invest in monitoring a mountain that has not erupted in living memory is a difficult sell. Especially in developing nations where resources are limited and immediate crises, like poverty, disease, conflict, take precedence over hypothetical volcanic threats. And so we watch some volcanoes closely and ignore others entirely. We wait for them to announce themselves before we pay attention. Sometimes that works. Sometimes we get weeks of warning, as we did at Pinatubo. Sometimes we get hours, sometimes minutes, and sometimes we get no warning at all. The challenge with supervolcanoes is that they do not behave like ordinary volcanoes. An ordinary volcano, a stratovolcano like Mount St. Helens or Vesuvius, shows clear signs before it erupts. Earthquakes increase in frequency and magnitude. The ground swells, gas emissions spike. Magma approaches the surface and its movement is detectable. But supervolcanoes are different. Their magma chambers are so vast, so deep, that detecting meaningful changes is extraordinarily difficult. Yellowstone's magma chamber sits 3 to 9 miles beneath the surface. It is not a single pool of liquid rock, but a complex mush. Small earthquakes happen constantly at Yellowstone, thousands per year. Most are magnitude 2 or less, unfelt, background noise. The ground rises and falls by inches over the course of years, but it has been doing this for decades, with no eruption. Is this normal variation? Or is it a prelude to something catastrophic? Scientists genuinely do not know. And herein lies the terrible paradox. The very size that makes supervolcanoes so dangerous also makes them nearly impossible to predict. In 2017, a team of researchers analyzed ancient magma from the Bishop Tuff, a supereruption that occurred 760,000 years ago. They wanted to understand how quickly the magma chamber assembled before the eruption. The answer shocked them: decades. Perhaps less than a century. For hundreds of thousands of years, the magma chamber had been cold, dormant, solid. Then, in a geological instant, fresh magma intruded. Temperatures rose. The mush began to melt. And within a human lifetime, the system went from dormant to explosive. If this is typical of supereruptions, then we may not have the thousands of years of warning we once assumed. We may have only decades. And decades, in the context of monitoring and preparing for a global catastrophe, is almost no time at all. The United States Geological Survey operates the Yellowstone Volcano Observatory. It is one of the most sophisticated volcano monitoring systems in the world. Seismometers detect every tremor. GPS stations measure ground deformation with millimeter precision. Satellite radar tracks changes in the caldera's shape. Scientists analyze gas emissions from the thousands of thermal features scattered across the park. If Yellowstone shows signs of an impending supereruption, we will know. Probably. But knowing is not the same as preventing. And even knowing may not give us enough time to prepare. An evacuation of the western United States would be the largest logistical operation in human history. Where would 10 million people go? How would we feed them, house them? Maintain order in the face of absolute catastrophe? There are no good answers to these questions. Only plans that sound reassuring on paper but would collapse under the weight of reality. And Yellowstone is only one supervolcano. It is not even the most dangerous. Campi Flegrei, in Italy, shows signs of unrest far more frequently than Yellowstone. The ground there has risen by over 6 feet since the 1950s. Earthquake swarms are common. The Italian government maintains a detailed evacuation plan for the region, but 500,000 people live directly above that caldera. And Naples, a city of nearly 1 million, sits just a few miles away. Could Italy evacuate 1.5 million people on short notice? Perhaps, if the warning came weeks in advance. If the roads remained passable. If panic did not overwhelm the system. But those are large ifs. The truth is that we are better at monitoring volcanoes than we have ever been. Our instruments are more sensitive. Our models are more sophisticated. We understand the warning signs. But understanding is not control, and monitoring is not prevention. We cannot stop a volcano from erupting. We can only watch it, measure it, and hope that when the time comes, we will have enough warning to save lives. At Pinatubo, we had that warning. 58,000 people evacuated. Science worked. But Pinatubo was not a supereruption. It was not global. And the next one might not give us weeks to prepare. It might give us days or hours. And in those hours, all our instruments, all our models, all our careful monitoring will be reduced to a single, terrible realization. The giant is awake. And there's nothing we can do but witness what follows. In the aftermath of catastrophe, humanity has always asked the same question. Could we have prevented this? After Pompeii, the Romans had no answer. They did not understand what a volcano was. They could not have known that Vesuvius would erupt. They were innocent in their ignorance. We no longer have that innocence. We know what volcanoes are. We know what they are capable of. We know with uncomfortable precision that a super eruption will happen again. And we know that when it does, it will challenge our civilization in ways we have never been challenged before. The question is no longer whether we could prevent it. We cannot. The question is whether we could survive it. Perhaps the deepest lesson Lake Nyos offers is about humility. For all our technological sophistication, for all our scientific knowledge, we remain vulnerable to the planet we inhabit. The Earth is not a stable platform designed for our comfort. It is a dynamic system driven by internal heat, shaped by chemical reactions, governed by forces that vastly exceed our ability to control. We can monitor, we can mitigate, we can sometimes predict. But we cannot eliminate the fundamental reality that we live on a restless planet whose processes occasionally align in ways that are hostile to life. Volcanoes will erupt. Earthquakes will shake. Storms will intensify. And yes, lakes will breathe out the gases they have accumulated in silence. The degassing pipes at Lake Nyos are not a victory over nature. They are a negotiation with it, a way of asking the Earth to release its pressure more slowly, more gently, in ways that do not kill. They represent the best we can do, not dominance but management, not control but coexistence. And in that acknowledgement lies perhaps the most important lesson of all. We are not separate from nature, not above it or beyond its reach. We are part of the system, subject to its laws, vulnerable to its disruptions. The safety we enjoy is never absolute. It is always provisional, always dependent on continued vigilance, continued investment, continued willingness to learn from disasters and act on that knowledge. Lake Nyos killed 1,746 people. But it also taught us that invisible dangers are still dangers. That beauty can conceal catastrophe. That the absence of past disasters does not guarantee future safety. That prevention requires resources, commitment, and the political courage to act on threats that have not yet materialized. The question is whether we are wise enough, humble enough, and committed enough to apply these lessons beyond this single lake in Cameroon. The Earth has more secrets, more hidden dangers, more combinations of processes that could align in deadly ways. Lake Nyos showed us one such combination. We cannot afford to wait for similar disasters to reveal the others. The vigil continues. There's a photograph taken in 2023 from the hills above Lake Nyos. In it, you can see the crater lake in its entirety, a near-perfect circle of deep blue water embraced by green crater walls. 3 white fountains rise from the surface, their plumes catching the afternoon light. From this distance it looks peaceful, almost serene. You would never know that beneath that tranquil surface lies a history written in silence and sorrow. Today, Lake Nyos exists in a state of managed equilibrium. The degassing pipes continue their ceaseless work, releasing approximately 60 million cubic meters of carbon dioxide each year. Monitoring stations positioned around the lake record water temperature, gas concentrations, and seismic activity. Solar panels power automated sensors that transmit data to research centers in Cameroon, France, and Switzerland. An emergency warning system connects to villages in the valleys below, ready to sound alarms if sensors detect dangerous changes. This infrastructure represents one of the most sustained hazard mitigation projects in modern geological history. Yet it exists in a state of perpetual fragility. The pipes require constant maintenance. The monitoring equipment must be calibrated and replaced. The data must be reviewed by experts who understand what subtle changes might indicate growing instability. All of this requires funding, expertise, and institutional commitment resources that are never guaranteed in perpetuity. Some survivors have returned to the land. They farm the same volcanic soil their grandparents cultivated, tend cattle in the same valleys. But they live differently now. They keep emergency supplies ready. They have designated evacuation routes to higher ground. They listen to the radio alerts and watch the fountain plumes with vigilance that previous generations never needed. Their relationship with the lake has changed from one of coexistence to one of wary cohabitation, sharing space with a neighbor they know could still turn deadly if vigilance falters. The younger generation born after the disaster carries a different burden. They know the story only through the telling, through the grief of parents and grandparents, through history lessons and memorial ceremonies. For them, Lake Nyos is both home and abstraction, a place of beauty shadowed by inherited trauma. Some choose to leave, seeking lives elsewhere, unwilling to accept the psychological weight of living beside a managed threat. Others stay, finding meaning in continuation, in the defiant act of building futures on land that once took so many. Beyond Cameroon, the lessons of Lake Nyos have influenced hazard assessment worldwide. Crater lakes in volcanic regions, from Indonesia to the Philippines, from Italy to New Zealand, have been surveyed for dissolved gas content. Some have been found to harbor dangerous concentrations. Monitoring programs have been established. Degassing systems have been proposed, though few have been implemented due to cost and technical challenges. Lake Kivu remains the greatest unresolved concern. The methane extraction project, which began in 2015, removes some gas while generating electricity for Rwanda. It is an elegant solution, turning hazard into resource, danger into economic benefit. Yet the extraction rate is still insufficient to fully degas the lake, and political complexity between Rwanda and the Democratic Republic of Congo complicates comprehensive management. The 2 million people living along Kivu's shores continue their lives in the shadow of potential catastrophe, most unaware of the invisible threat accumulating beneath waters they use for fishing, transportation, and recreation. This is perhaps the most unsettling aspect of limnic eruption hazards. They can exist for decades, even centuries, in plain sight, unrecognized by the people most at risk. Unlike a smoking volcano or earthquake-damaged buildings, an oversaturated lake provides no visible warning. It looks beautiful. It seems peaceful. Only sophisticated scientific instruments can detect the danger, and only informed interpretation of that data can assess the risk. We have learned since 1986 that the Earth contains more ways to kill than we had previously imagined. We have developed technologies to monitor and mitigate some of these dangers. But we have also confronted the limits of what technology alone can accomplish. Sensors can detect danger, but they cannot compel action. Engineering can reduce risk, but it cannot eliminate it. Knowledge can inform decisions, but it cannot guarantee that wise decisions will be made. The story of Lake Nyos is ultimately a story about time, about the collision between geological time and human time between the slow accumulation of danger and the sudden moment of release. It reminds us that patience is not a uniquely human virtue. The Earth, too, is patient. It accumulates pressure over decades, over centuries. It stores energy in forms we cannot see. And when the threshold is finally crossed, when equilibrium can no longer be maintained, it releases that energy with neither warning nor mercy. On quiet nights in the villages below Lake Nyos, people sometimes pause to listen to the distant sound of the degassing fountains, a constant white noise, like rain or wind that has become part of the landscape's voice. That sound is reassuring. It means the pipes are working, the gas is being released, the danger is being managed. But it is also a reminder that management is not resolution. The earth beneath the lake continues to produce carbon dioxide. The magma chamber has not cooled. The fundamental hazard remains, held in check by human intervention that must continue indefinitely. There is a word in the calm language that survivors use when speaking of Lake Nyos. It translates roughly as the place that must be watched, not the place that was dangerous or the place that killed. Present tense, continuous action. A recognition that some threats do not end, they simply enter a different phase, one that requires eternal vigilance. This, then, is the final lesson Lake Nyos offers. Safety is not a destination. It is a practice, a commitment, a choice made daily to maintain the systems and structures that stand between vulnerability and catastrophe. It requires resources, yes, but also something more, the collective will to protect even those who do not yet know they are threatened, to invest in prevention even when the return cannot be measured in profit, to remember lessons written in tragedy even as time softens the edges of grief. The degassing pipes will fountain for years, perhaps decades, perhaps centuries. They will require maintenance and monitoring for as long as people live in these valleys. They stand as monuments to both human fragility and human resilience, proof that we can learn from disaster, that we can act on knowledge even when certainty eludes us, that we can, if we choose, tend the dangerous beauty of the world we inhabit with wisdom and care. Lake Nyos sleeps now, but it is a supervised sleep, watched over by sensors and scientists, by pipes that breathe for it, by people who remember what happens when the earth exhales and no one is prepared to hear it. The vigil continues. It must. For beneath the surface of quiet waters, in the darkness where human eyes cannot see, carbon dioxide still seeps upward from the deep places of the earth, and it will continue to do so long after we are gone, long after our pipes have rusted and our sensors have failed, long after memory of August 21st, 1986 has faded into legend. The earth is patient, and we must be vigilant.